Going on, everybody? It's Mr. Gustin. I'm back in the physics classroom. The weather outside is frightful, but it's certainly not December. It's February, day after Valentine's Day, and so I just got to make sure I get this lab done for you guys just in case, for whatever reason, we can't come to this lab in class. So here's what I got for us. This is our Windmill Lab. We've used these windmills before. The windmills of this time are set up vertically, and there's a string attached to it. That string is then attached to a mass on the ground. I'm going to try and get all this in the frame at the same time. Move this table back so you can see it all, right? So this mass is a 100-gram mass. It's sitting down here at the table, or sitting down here at the ground. And what I can do here is as I spin this thing right here, I can wind up my string, and if I let it go from rest, this thing will rotate down to the ground. The weight of that mass creates tension, and that tension pulls and causes the torque, and that torque causes it to accelerate rotationally. Now, the falling motion and the rotating motion are equal here. And your task in this activity is to find the rotational inertia of this object. However, it's not a regular object, so we're not going to find this I value or this moment of inertia's equation anywhere in our packet or online. So I need you to solve for it, taking some data. So what we're going to do is change the weights or the hanging masses. We'll change those, and we'll take some measurements. Some of those measurements that we're going to take, let's go ahead and check it out. So what are some things I could take measurements on? Well, obviously, I have a set of masses right here, so I'm going to need those. I'm also going to probably need the pulley's mass. Do I want the pulley's mass? I don't want the pulley's mass. I want the pulley's radius, definitely, how big the pulley is. In particular, where is this thing located? What is the radius of the pulley where the torque is being applied? Okay? So let's go ahead and start thinking about some of those variables. Let me get a measurement tool, a meter stick here, and we'll start gathering some data. So the radius that this tension is going to be applied at is about 14, what am I looking at here? 14 interior, not 14, what am I, crazy? 3.8 centimeters. I'm going to go ahead and start taking some data on the board. It's not Friday. Happy Wednesday, not Friday. On the board, let's take some data. Radius of the tension, I said, was 0.038 meters. That's there. That's something I need to know. All right. What else do I have to know? That's probably about it. And then in my packet, some of the data that I'm going to take is the various masses. So what's the hanging mass in kilograms? I need to know the time for fall. As I release this thing from rest, how long does it take to hit the ground? I kind of want distance, either distance of fall or number of rotations to fall. Either one of those will help me. And then I'm going to probably need to find, somehow calculate angular acceleration or acceleration. So either A or A, and force of tension. These are some things that I'm going to need to know. And then eventually I'll probably need to find torque. So probably a third one over here will be something I should do also. So force of tension, and then over here we'll do torque without, you cannot do I times alpha because I don't know I. And the goal here is to find I using a graph. And so if I'm going to find I using a graph, I want to graph torque over here and alpha over there. This will help me use a slope value to find my I value. We'll come back to that later. It's most important that we get our data right now. So let me show you how I'm going to do this. In order for us to kind of minimize variability between the masses, all I'm going to do is we can kind of see how this thing is cranked up right now. Okay, we see that the mass is on the ground. But all I really need to do at this point is start this arm or arm of the pulley up and rotate it around a couple times. If I go 3 times, let's go, that's 1 rotation, that's 2 rotations, and that's 3 rotations. So right now I have the arm, or this arm of the pulley up. When this thing comes around a 3rd time, I can stop my timer because it will have fallen 3 rotations. That allows me then to take some consistent data between every trial. I don't need to keep measuring height and whatnot. I just know it's rotated up 3 circumferences of this thing, and you already know the radius, so 2 pi r that thing, and you've got your linear and angular displacement. So at home, your job is going to be to time how long it takes for this thing to make 3 rotations for a given mass. Okay? So that's where we'll start. But we're going to end up starting with some smaller masses. Not the biggest mass. We'll go smaller to bigger, so hopefully you get a sense of our timing system before you go ahead and start. Let's start with 20 grams. Let's see what 20 grams gives us, if 20 grams is going to give us something. All right, there's 20 grams. Does 20 grams rotate my system? It does not. There's too much internal friction. 20 grams is too light. Let's try 50. 50 grams will give us a little rotation, I think. Heck yeah, there we go. All right, 50 grams is enough to get us some rotation there. So I'm going to start this arm up. Let's go 3 rotations up. Ready? That's 1 rotation up, 2 rotations up, 3 rotations up. All right, we're going to start our timers in 3, 2, 1, go. We might be here a while, but what we do notice is it starts slow, and it does, in fact, accelerate. Like we are literally witnessing acceleration of this object. We're almost there, and I think we are about there. That was it, okay? There were your 3 rotations. Did you get it? Did you count? Or were you listening to me? Hopefully you were counting rotations and watching very closely, but that was a 50-gram mass. How many kilograms? 0.05. 0.05. Let's go add it to our data table so we have that. 0.05 kilograms. That was the first one. Next one's going to be the 100-gram mass. We're going to double it up. We're going from 50 to 100. Here we go. These things will start to go faster, or I expect them to go faster from here on out. Okay. 3 rotations. We'll go 3 rotations from here. Ready? And 1, and 2, and 3. And we're going to start in 3, 2, 1, go. That's 1 rotation, and 2, and 3. That's it. Got it? That was our second one. That was the 100-gram mass, or 0.1 kilograms. Whoa, it's still connected. 0.1 kilograms. Let's add that to our list. 0.10. Let's go 200 kilograms, or 200 grams. Where's my 200-gram mass? There it is. 200 grams. Latch it on. Get your timer set. You're recording mass and time right now. Ready? Let's go from here. And 1, 2, 3. And we're dropping in 3, 2, 1, go. 1 rotation, 2 rotations, and there's your third one. That was 200 grams, 200-gram mass, 200-gram mass. Do we have a 300-gram mass? We don't, but we do have a 1 and a 2. We'll attach both those masses together. We want to get 5 to 6 good data points here, so we got a wide variability of data. All right, let's go from here. Ready? Just 300 grams. 1, 2, and 3. Get your timer set. We're starting in 3, 2, 1, go. 1, 2, and 3. There you go. was 300 grams. 300 grams. Next up, we're going to go 500 grams. You know what? I made a mistake. The last one was actually 400 grams. So edit that. That was 400 grams. As I was putting the masses away, I just realized what had happened. That was 400 grams. This one is 500 grams. This one is 500 grams. So I'll make sure I record it properly on our data table. That was 0.4. Then we'll go 0.5. We'll go 0.7. And then 1 kilogram. Remembering that our distance is 3 rotations the whole way down. This one's 500 grams. All right, let's see some tension in it. 1, 2, and 3. Let's get this thing to stop swinging so much. Settle on down. 3, 2, 1, go. 1 rotation, 2 rotations, and 3. There it was. Okay. That was our 500. And then we said we're going 700. Tack on a 200 gram mass right here. Uh-oh, lost it. Okay, I keep losing it. This is like a comedy sketch right now, kids. I keep losing this thing. Get on there. This is ridiculous. Okay, let's get some tension in this guy. There we go. We'll start from right here. And 1. Ready? 3, 2, 1, go. 1, 2, 3. That gets really fast. 700 is really, really fast. It's kind of hard to see at some point, but that was it. That was 700. Okay? Our last trial, our last one. You can actually still see it rotating pretty good. Last one is the 1 kilogram mass, the big one, the granddaddy of them all. Here we go. 1 kilogram mass. You know it's going to go quick, so have your thumb on the timer. Be ready to go. Let's get some tension in this guy so don't break anything. We'll start from here, up. 1 rotation, 2 rotations, 3 rotations up. Here we go. Settle on down, settle down, settle down, settle down. 3, 2, 1, go. 1, 2, and 3. That is real quick. I'm not even going to go near the blades because they're spinning so quickly. Get this thing off of there. Bang. All right. At this point, we have a data table kind of already set up for us. We have our hanging masses, all of these. You should have times for all of them. If you don't, go back and get them. You also have got the distance. We know it rotated 3 times. Here's our radius. 2 pi r tells me both the angular displacement and the linear displacement of this thing. You've got time. You've got distance. You should be able, initial speed, you have these things. You should be able to find acceleration, both angular and linear. You should be able then, with the mass of the hanging masses, you should be able then to find the tension force that was acting on the masses. You know the mg, you know the ft, right? If I think about the masses themselves, the masses had a weight force pulling down, they had a tension force pulling up. I can write an F that equation. I should have that figured out or be able to figure out what Ft is. M times A equals mg minus Ft. You can find that. And then torque is just tension times force of tension times the radius, because here's my pulley, there's my tension force, which is the same as that tension force acting at a radius that we already measured. We should be able to figure that out. From here, this data should be enough for you to complete the lab and figure out what is the rotational inertia or the moment inertia of this crazy windmill-looking object. If you got questions, drop in the comments, send me an email, ask me in class. Until next time, see ya!